the idea behind remainder theorem and factor theorem and how to use these two theorems to solve problems. Recall that division algorithm says dividend equals divisor times quotient plus remainder. So for now, we're going to use f of x, q of x, and r of x to denote dividend, quotient, and remainder respectively. So keep in mind, these are polynomials. And for now, we consider the divisor to be a linear factor in this form, being x minus c. With this setup, we rewrite the polynomial f of x as the product of x minus c and q of x plus a remainder term being r of x. We can evaluate this function by substituting x with c as we did before. So basically this says f of c equals to c minus c times q of c plus r of c. C minus c equals 0, so 0 times q equals 0. 0 plus r of c equals r of c. So this says the function value at x equals c equals to the remaining term, which is a remainder. And this is a result from the remainder theorem. So this gives us another tool to evaluate the function instead of substituting x with a specific value and evaluate the function with the original form. We can simply evaluate the function value at this specific number by determining the remainder we would get if we divide the polynomial with a linear factor with 0 being the c. Okay, so let's see how this is going to work. So consider a polynomial which is a quartic polynomial, meaning fourth degree polynomial in this form, and we want to evaluate f of 5. The remainder theorem says to evaluate this function, this number, we can simply divide this polynomial with a linear factor being x minus 5 and determine what the remainder is going to be. The remainder is going to be a constant. That constant is going to be the function value. So synthetic division start with writing down the coefficients of all terms in decreasing order for variable x. There's no missing order in this polynomial. We're going to start with the leading coefficient, which is 1, followed by the coefficient of the cubic term, 1, and then the quadratic term, -6, linear term, -5, and constant term, -15. And then we drew a little box to enclose the number 5 that we want to evaluate the function at. And we start the synthetic division process. We drew down the leading coefficient 1 and use 1 to multiply by 5, give us 5. You bring this 5 above this line and then adding up the numbers along this line and bring it down. That's give you 6. 6 multiplied by 5 give you 30. 30 plus -6 give you 24. 24 multiplied by 5 bring us up, give you 120. And the 120 add to -5 give you 115. 115 multiplied by 5 give you 575. And 775 give you 575, and 575 add up to -15 give you 560. That's going to be the remainder. And by the theorem, we know that this remainder after the synthetic division is going to be the function value at 5. Sometimes it's convenient to do so, especially when the degree of the polynomial is high. For example, in this case, it is a degree 4 polynomial. If you choose to evaluate the function by substitution, you have to raise 5 to power 4. That's going to give you a large number. This is going to be a lot more at this point. It seems to be comparable with regards to efforts, no matter you evaluate the function by direct substitution or through synthetic division. The advantage of using synthetic division is going to be a lot more clear if we have to cope with a much larger degree polynomial. For example, a 10th degree polynomial, and evaluated at say x equals 11. At that point, using synthetic division is going to be a lot easier to get the function value compared to substitution. So not only we can evaluate the function at the rational number, and we can do it at an irrational number. For example, root 7. And the procedure for synthetic division is the same. You write down the coefficients for a polynomial in decreasing order of power x. And then you enclose the 0 in a box. Okay, this means to be root 7 instead of 7, and you start the process. And eventually you got a remainder. This remainder happens to be 0. That says root 7 is x value. That's going to make your function being 0. By definition, root 7 is going to be 0 of this polynomial. Okay, so that's why the answer to this question is going to be yes. It's asking, is this a 0? Yes, it is 0 because the function value is 0. Okay. Synthetic division not only works for rationals, irrationals, it works for complex number as well. So, as I said earlier, the process is the same. It's just algebraically, you have to deal with complex numbers. So computation-wise, it's going to be slightly more complicated. Okay, so you bring down the leading coefficient. We want to check whether 3 plus I is a 0 of this polynomial. Bring down the leading coefficient being 1. 1 times 3 plus I give you 3 plus I. Bring it upward. And then add up numbers in this line give you negative 4 plus I. Negative 4 plus I multiply with 3 plus I. I did the calculation on the right hand side. So if you go through the following process, you will get the product being negative 13 minus I. I bring this number up and add all number in this line. That gives you 3 minus I. 3 minus I multiply with 3 plus I give you 10. And then add numbers in the very last column, you're going to get 0. Since the function value at x equals 3 plus I is 0, by definition, 3 plus I is a 0 of this polynomial. So the answer is yes. Okay, so this is application for the remainder theorem. A direct consequence of this is that if the remainder is a 0, as we have seen from the previous examples, that says the function value at that specific number is a 0. That means the divisor x minus c is going to be a factor of that polynomial. And it goes both ways. If the function value is 0 at x equals c, we can say x minus c is a factor. Alternatively, if x minus c is a factor, then f of c is 0. This result, as a consequence of the remainder theorem, is called the factor theorem. And we can use the factor theorem to check whether a particular linear form is a factor of a certain polynomial or not. So basically, we're going to go through the synthetic division process and check whether the remainder is going to be exactly 0. If the remainder is 0, that means the function value is 0. That means that divisor is going to be a factor. Okay, so in this example, we're going to show the process to determine whether x plus 3 is a factor. So write down the coefficients in decreasing order for the degree of the variable x. It's going to be 2, negative 13, 10, negative 25, 6. So there's no missing order, no missing power. So we don't have to worry about put down 0 as a placeholder. Okay. In a little box, you enclose the 0 of the divisor. In this case, the divisor is going to be x plus 3, so 0 is negative 3. So we put negative 3 inside this little box and then start the synthetic division. You bring down 2. 2 times negative 3 gives you negative 6. Add the numbers in this column, give you negative 19. Negative 19 times negative 3 give you 54. You add up. That's going to give you 64. You continue this process until you determine the remainder. The remainder turns out to be 675, which is not 0. That means x plus 3, which is the divisor, is not going to be a factor, but a factor theorem. Because if it is a factor, we should expect the remainder being exactly 0 by the factor theorem. Okay, this is one example to show you how to apply the theorem, a factor theorem, to determine whether a linear form is a factor. In the next example, I'm going to show you how we can write down the polynomial of a certain degree with given zeros. I have a polynomial which is degree 3 with zeros being 1/3 and plus minus root 3. By the factor theorem, for each zero of the polynomial, there will be a corresponding linear factor. When the 0 is 1/3, the corresponding factor is going to be x minus 1/3. 0 is root 3, the factor is x minus root 3. 0 is negative root 3, the factor is going to be x minus negative root 3, which is x plus root 3. And you multiply all those three factors together, it's going to be like this. And we do have a free parameter a here. This a is a free parameter which can be anything except 0. So any polynomial in this form is going to have zeros being these three numbers, and it's going to be degree 3. And it's only asking for one possible polynomial, so a really can be anything other than 0. So let's say a equals 1, then that's going to give us a specific form for a good polynomial that's going to satisfy all conditions. And we're done.